Hey friends, so today is the last lesson in curve sketching, and really it's just a putting it all together sort of a lesson. We have done everything we need to except one final step, and one final step is really just, hey, let's take all these points that we just figured out how to get, and let's take this knowledge of how the graph is increasing and decreasing and concaving up and concaving down, and let's actually draw the graph. Okay, so in a way, we're adding in the drawing the graph portion today, but it will be a review of everything you've done in the unit to date. Okay, so we are now going to put together all the tools we've learned about to analyze function. The process for analyzing includes the following. You're going to determine the domain. These are the things like, I'm going to ask you questions where it just says analyze the following, and you're going to have to list these things, okay? You want to determine the domain. You want to determine the zeros, the x-intercepts, and the y-intercepts, and determine any symmetry, okay? Then you want to talk about asymptotes, horizontal, vertical, and slant, if applicable. Then you want to use the first derivative test to determine where the function's increasing or decreasing. A reminder, when you determine the asymptotes, make sure for vertical asymptotes, you're checking one-sided limits, and for horizontal asymptotes as well. So you're checking to the, so for vertical, you're checking to the left and to the right of whatever that non-permissible value is. For horizontal, you need to check positive infinity and negative infinity, okay? Then you're going to use the second or first derivative test to determine the relative extrema. Then you're going to use the second derivative test to determine concavity and possible points of inflection. And then you're going to use all that information, pull it together, and actually draw the function out. Okay, so first one we're going to do, analyze and sketch the following function. F of x is x squared minus 1 all over x squared minus 4. So probably we want to factor that right away, just so we can see it in factored form. I got two difference of squares there. So I've got x plus 1 and x minus 1 over x plus 2, x minus 2. Okay, so first thing to talk about is the domain. The domain will be x is a member of the reals, but it can't be plus or minus 2. Now, we're going to write that in interval notation, though. So that will be negative infinity to negative 2 in union with negative 2 to 2 in union with 2 to infinity. Okay. Okay, intercepts and symmetry. Well, I know that I have x-intercepts with a rational graph. I know I have x-intercepts with the factors on the top. So that'll be plus and minus 1. I know I have y-intercepts if I just plug 0 in for x. So plugging 0 in for x is going to give me positive 1 over 4. Okay, so I have x-intercepts at negative 1 comma 0, 1 comma 0, and y-intercepts at 0 comma 1/4. Now, to test for symmetry, that was one of the first things we talked about. So we want to take a look at what f of negative x would be. So if I replaced x with negative x here, I would still actually get x squared minus 1 over x squared minus 4. So f of x equals f of negative x, which means this is an even function, which means it's symmetrical about the y-axis. Okay. Awesome. Okay, so now we're going to go into asymptotes. Okay, so I know that for my vertical asymptotes, I want to test plus and minus 2. So I need to go to the left of negative 2 and to the right of negative 2. I need to look at the limit to the left of 2 and to the right of 2. So I'll give you a sec to do that. Okay, and we would find that the limit to the left of negative 2 is infinity. The limit to the right of negative 2 is negative infinity. So that concludes, yes, I have a vertical asymptote there. The limit to the left of positive 2 is negative infinity. And the limit to the right of positive 2 is positive infinity. And so again, I have a vertical asymptote there as well. So I have vertical asymptotes at x equals negative 2 and x equals 2. Okay. Then for my horizontal asymptotes, I need to divide everything by the highest power I see in the denominator. So I'm dividing all my terms here by x squared. Okay, that ends up being 1 minus 0 over 1 minus 0, which is 1 over 1. which is 1. Then to the negative infinity portion, same thing, and I get 1. Okay, so I have a horizontal asymptote at y equals 1. There is no oblique asymptote here because the degree on top is not larger, right? Okay, so I'm looking for intervals of increasing and decreasing for the function. I need to take the first derivative in order to do that. So I'm looking at the quotient rule here. So I'll be looking at the derivative of f times g minus f times the derivative of g all over g squared. So the derivative of f is 2x times x squared minus 4 minus f x squared minus 1 over the derivative of g, which is 2x, all over x squared minus 4. Okay, so this is now going to become 2x cubed minus 8x. And this will be, I'm just going to count this as negative 2x. So that'll be negative 2x cubed plus 2x. Okay, and so then I end up with negative 6x over x squared minus 4. Okay, just in case my head hid that, it's right here. Okay, so now I want to look for my critical numbers. So my critical numbers exist when the derivative equals 0 or when the derivative doesn't exist. I know the derivative doesn't exist at plus or minus 2, and I know the derivative equals 0 at 0. So I have critical numbers at negative 2, 0, and 2. Now, some of you may be out there listening to this saying, okay, but I should ignore negative 2 and 2 because it didn't exist in the original function. Now, you're right, it didn't exist in the original function. But the fact that it doesn't exist in the original function tells me it can't be a max or a min point. I still want to plot these guys on a number line because I still need to see whether I change from increasing to decreasing at that moment. Plus, you already know, based on your knowledge of rational functions, that at negative 2 and 2 right now, I've got a vertical asymptote, right? Well, at a vertical asymptote, I'm neither increasing nor decreasing. So even if I get the same on both sides of negative 2, I still want to split my increase and decrease portions up so that I'm not actually including negative 2 because nothing's happening. The original graph doesn't exist at negative 2 and positive 2. So I can't say I'm increasing or decreasing at negative 2 or positive 2. Okay, so the fact that they don't exist on the original function tells me I don't have a max or a min point, but it also tells me that I can't include those moments when I'm talking about intervals of increasing and decreasing. Okay, so I'm going to plot negative 2, 0, and 2 on a number line. I'm going to test to the left of negative 2, in between negative 2 and 0, in between 0 and 2, and 2. Okay, that should give you plus, plus, minus, minus. So that means I'm increasing from negative infinity to negative 2 in union with negative 2 to 0. Okay, I can't just say negative infinity to 0 there because I don't exist at negative 2. Then I'm decreasing from 0 to 2 in union with 2 to infinity. And now I'm looking for my max or my min. To do my max and min, I'm looking for a change in increasing to decreasing or change in decreasing to increasing. I have one right at 0 here. So that's going to be a local max at 0 comma something. Well, how do I get my something? I plug that back into the original equation and I get my y value. If I plug 0 back into the original equation, I get a y value of 1/4. So I know that I have a maximum at 0 comma 1/4. My local max happens to be at my y-intercept for this guy. Okay, so now I want to take a look at concavity and possible points of inflection. In order to do that, I need the second derivative. So I'm taking a look at the first derivative. I need to take the derivative of the first derivative. Again, I'm looking at the quotient rule. So I'm looking at derivative of f times g minus f times derivative of g all over g squared. So derivative of f would be negative 6 times g minus f, which is negative 6x. Now the derivative of g is the chain rule. So I've got 2 times x squared minus 4, and then times the derivative of the inside function, which is 2x. On the bottom, I have g squared, which would be x squared minus 4, all to the 4 now. Okay, so now I want to start cleaning this up a bit. Negative 6 would be positive 6x. times 2 is 12x, and times 2 is 24x. I'm going to go ahead and I'm going to factor out an x squared minus 4. Okay, and now I'm just going to clean this up a bit. I'm going to distribute my negative 6 in here. So this would be negative 6x squared plus 24 plus 24x squared. And then when I add those together, I end up with 18x squared plus 24. Now, where did that x squared minus 4 go? X squared minus 4, and one of these x squared minus 4s divided each other out. So that's why I was left with the x squared minus 4 to the 3. Okay. All right, so one last thing I'm going to do to this guy is just factor the 6 out of the top, and that's going to leave me with 6 times 3x squared plus 4 all over x squared minus 4 to the 3. Now, to check important numbers for concavity and points of inflection, again, that's where the second derivative would equal 0 or wouldn't exist. When I go to set that equal to 0, there's actually no points where this could equal 0. So because of that, there will be no inflection point, okay? I do need to test concavity though. So I'm checking plus or minus 2 from where it doesn't exist. So I'll check to the left of negative 2 and between negative 2 and 2 and to the right of negative 2, okay? And so I end up with plus minus plus there. And so I can concave down between negative 2 and 2 and concave up from negative infinity to negative 2 in union with 2 to infinity. Okay. Now, the last step in this question is just to draw the graph. So I'm going to take all of this knowledge. I know that this was an even function, so my graph should look symmetrical about the y-axis. I know I have 2 vertical asymptotes. I know I have a horizontal asymptote. I know I have a maximum point. I know I'm concaving up on essentially the left and right side of my asymptotes, my vertical asymptotes, and then in the middle, in between those vertical asymptotes, I should be concaving down, which makes sense because I had a maximum point in that region as well. I also have my x-intercepts and my y-intercepts to graph. Now my maximum and my y-intercept are the same in this one, but I want to look at all the points to graph. I want to look at the intervals of increasing and decreasing. I want to look at concavity. I want to look at possible points of inflection, and then stick all that together in a drawing. So you go ahead and try and draw it before I show you mine. Okay, and here's what the drawing should have looked like. Okay, so we are concaving up here and down here. We're increasing all the way up to here, and then we're decreasing from there to there. Whoops, sorry, I didn't mean to go to that guy yet. Okay, so that's what your graph should look like. When you're drawing me a hand-drawn sketch as well, you want to make sure you label all the points with the actual coordinate pairs on your drawing, okay? All right, good. Next guy. Given the graph of the derivative of f of x, so this is not the original function, this is the derivative, we want to describe and sketch the original. We want to try and figure out what the original must have looked like. Okay, so here's some things I know. I know that the function has a minimum at a and at e, okay, because that's where I'm switching from negative to positive in the first derivative, right? When I switch from a negative first derivative to a positive first derivative, I know that I'm switching from decreasing to increasing, so I know I must have a minimum point there. Likewise, at c, I should have a maximum point. Okay, so just trying to take stock of all the little things we know so that we can try and put this together. So I know that the function's increasing from a to c in union with e to infinity. And then I know that it'll be decreasing from negative infinity to a in union with c to e. Okay. Okay, now let's take a look at what maybe the second derivative looks like. Now the second derivative would be the derivative of this guy. So where I see the max and the min points, I know that that will be an x-intercept. Okay, where the first derivative was increasing, I will need to be positive, and where the first derivative was decreasing, I will need to be negative, okay? So now I know also that I have a point of inflection at B and at D. So this guy here and this guy here are going to be my points of inflection because the second derivative is 0 and changing concavity, okay? So I want you to pause me, see if you can put all those things together and come up with a drawing. Okay, and the drawing you should have gotten is something like this. Okay, how'd you do? Okay, we're going to do another analysis now. Sketch the graph of f of x equals x cubed minus 3x squared plus 4 without graphing on your calculator. So, same procedure. First thing we're going to do is determine the domain. This is a polynomial function, so it'll be real. Okay. Then we need to take a look at intercepts and symmetry. Well, for intercepts, I know I have a y-intercept at 4. For an x-intercept, I need to find a first factor, essentially. So I might want to test p of 1, p of 2, p of -1, p of -2 until I find a factor, right? I can't go and factor this like a trinomial. Just be careful of that because it's an x cubed in front, not an x squared in front, right? Okay, so f of -1 happened to equal 0. So that tells me that I have a factor at x plus 1. I go ahead and divide. I'm not showing you the division here. You can do the division on your own, but that's going to get me x squared minus 4x plus 4. That now will factor into x minus 2l squared. Okay, so now I know I have intercepts. I have x-intercepts at -1, 0 and at 2, 0, and I have a y-intercept at 0, 4. As far as symmetry goes, the first thing I want to do is plug -x in, but that's actually going to change things, right? If I plug -x in here, that's going to give me -x cubed minus 3x squared plus 4. So f of x does not equal f of -x. But now that I know what f of -x equals, I want to look at negative f of x and see if those are the same thing. Now, if you are following, they won't be the same thing because this ended up staying negative at f of -x. And for negative f of x, this will switch and this will switch. So it's not, it's neither even nor odd. Okay, so there's no symmetry there. Okay, now I didn't actually say that here, but I would actually at this point say no symmetry. Okay. Okay, so now increase and decrease. I need to get the first derivative. So that'd be 3x squared minus 6x. Where does the first derivative equal 0? Well, I can factor out a 3x, and then I'd be looking at 0 and 2. So I want to plot 0 and 2 on a number line and check to the left, in between, and to the right. That's going to give me plus and minus and plus. Okay, so that means I am increasing from -infinity to 0 in union with 2 to infinity, and I'm decreasing from 0 to 2. It also tells me that I have a increasing to decreasing, so I have a local max at 0, something, which in this case would be 0, 4. And I have a local min at 2, something, plug 2 in to get out 0. Okay. So I now know my intervals of increasing, decreasing. I know my local max. I know my local min. Now I want to look at concavity and possible points of inflection. So I have to get the second derivative. Second derivative would be 6x minus 6. Where does that equals 0? My important point to check would be at x equals 1. Plot that on a number line and check to the left and to the right. And I end up with negative on the left, positive on the right, which means I'm concaving down from -infinity to 1. I'm concaving up from 1 to infinity. And it also means I have a point of inflection at 1, plug 1 back into the original equation to get out your y value. Okay, so point of inflection at 1, 2. All right, so now you pull all that together, label your important points, think about when you're increasing and decreasing, think about when you're concaving up and concaving down, go ahead and draw me a picture. Remember to label your each of the important points that you've discovered. Every coordinate pair point that you have should be labeled on your diagram. Okay, pause me and go do that. Okay, and the picture you should be looking at is something like this. Okay. Awesome. Okay, so that's what we're doing for the next couple of days. And this is your homework for you. And if you have any questions, by all means, make sure you come and see me. Okay, take care, guys.